I put in this example, but it's not really an example because I didn't want to solve it all the way through. But I did want to introduce the thought process and how we could have like combinations of principles that we in a very complicated problem that we might have to think our way through. This is the engineering thought process that we're learning right here. All right, so we have this block. It's a 2 kilogram block, and it's pushed up against a spring, some amount, right? X. So we've compressed up this spring, and it's released, and it slides down this thing, this slope right here. And if we wanted to make it, yeah, we did make it difficult. There is friction involved. Ooh. So it's gonna be slowed down by the friction, and it's going to eventually it's gonna hit this sphere that's on a rope that doesn't extend, right? So it's gonna act like a pendulum. So it's gonna start to swing up, let's see, the coefficient of friction between the ground is 0.2. The distance A slides from the unstretched spring is 1.5 meters, and the coefficient of restitution between the block and the ball is 0.8. And we know that the tension of the rope is 20 newtons, and then we also find out that the pendulum is going to go up and alpha equals 30, and we want to determine the initial compression of the spring. So we have like a whole series of events, and we have to think our way through them. And I can't stand that this thing is trying to zoom in and out onto the thing. It's getting very like, I can imagine what it's like for you. So, so we want to think through, so I wrote this down, think through this problem. All right, so first off, use Newton's second law at let's see, knowing that the tension of the rope, so we know the tension of the rope right here, right? They told us the tension of the rope when it's at right here, right? So that's not necessarily, has it stopped at this point. So you go, wait a minute, can I use work and energy right here? Not really, because we don't necessarily, we don't know the velocity right there, so we can't quite get that, but we could use Newton's second law, and we might want to call these things at different steps. We want to go this. Let's say that this is 1. Let's say that when the block here is 2. Let's say just after the collision is 3, and let's call this part 4. So we can go Newton's second law at state 4 of the block right here, and we could say, we could use the we'll use in the normal and tangential coordinate system, and then we could find v squared over rho right here, knowing the mass of the sphere, right? We could use this for the accelerate. We would get the acceleration from the tension, right, in the tangential normal direction, right? So in the normal direction right here, we're going to have, and we want to do FBD and IBD to do that, but then we could find the velocity of the ball of the sphere, and I'll call it S at 4 right here. So okay, so now we can figure out, we can use work energy at 3 and 4 to get the velocity of the sphere at 3. Right? We can go back to 3. So we found the velocity here, v sphere 4. So now we could find v sphere 3 right here, and then we can use impact or impulse and momentum at 2 and 3, between 2 and 3, right here, to figure and coefficient of restitution. Because we have a velocity here, we could figure out what the initial velocity of this has to be in order for this thing to go. So we're actually working through the thing backwards. And then, so once we have the velocity, we'll be able to get the velocity of 2 right here, and then we can use work energy at 1 and 2 to find the PE that's due to the spring. But also we need to be careful because we also have a PE that's going to be based on this right here. And we're also going to have a little bit of the friction, right? Because the distance that this thing is going to move right here is going to change. We already know D, but we also need to know X. So the distance that we're going to have energy loss due to friction is going to be X plus D. So this would be a really long problem to do. I'm not going to take up class time to do it, but we could definitely work our way through and think our way through the thing and come up to an answer. So I already described this. It already took me 6.5 minutes to do. If I were to continue to work on this problem, it would probably take me about a half hour, maybe. But this is a good problem. I like this problem a lot. And if we were to just put, I didn't have the solution manual for the edition that had this in here, but I found it on Chegg. I didn't like their edition here, but it goes on and on and on and on. For the description onto the thing. It's a long problem right here, but they do figure out the initial compression is 0.1071 meters right here. Maybe I'll just talk through the Chegg thing. Probably try to use Chegg for a legitimate purpose here. So I'm not sure. I don't think this is from the solution manual, but whoever did this wrote the thing up. And here's their general guidance as they talk through the thing. By the way, I didn't. I just thought my way through the thing. I didn't read this, so I haven't read this yet. By the way, so they talk about some vectors coming up right into here. Yeah, and they use parallel axis theorem. Oh, that's interesting. This is actually, they're talking about rigid bodies right here. So whoever's answering this, they don't realize where they're talking about to the students yet. So here's the step by step right here, right? So and they also didn't draw their inertial body diagram right here. They decided to use this old style of things where they reverse the direction of the inertial forces. It's called D'Alembert's principle, and it's one of the ways that I learned dynamics. But it's much better to learn dynamics using the inertial body diagram. So I'm not even going to continue with the Chegg thing because it's crap, right? The people that write that stuff, God help them. This is like their side hustle. These are like you can have a chauffeur, or you can have an Uber driver, right? Chauffeur, Uber driver. Nothing against Ubers. But if you could have a chauffeur and you're paying for a chauffeur, use the chauffeur, not the Uber driver. So, challenge accepted. I don't have an infinite amount of time, but I'm going to solve this damn problem because I'm a problem solver. I know how to solve problems, and so let me write down some of this work, demonstrate how I would go here, and I'm going to see if I'm going to get the same answer as them. Because I'm not afraid of a challenge, right? So first thing I'm going to do is I'm going to do my FBD and my IBD. And I'm going to use normal and tangential direction right here. And my angle is going to be 30 degrees. So I believe, let me double check right here. Yeah, here's our angle, so that's the angle right in there, right? So we're going to draw this thing up. And here's the tension that we happen to know. Here's the gravity that's working against us. So that's going to be 1 kilogram times 9.81, working right there. And there's our right here. And our Ft, we were told, is 20 newtons right here. So that's 20 newtons that's taking place. And this is going to be equal to, and we don't know the acceleration. It's probably in the tangential direction coming right here, but we hardly even care. Right here is where we're going to go. Mass times, and this is the mass of the ball, which I will call the sphere. I'll call it, oh, it is B. They labeled it B, so that is B. So the mass of B times the acceleration of B in the normal direction. And this should be, if labeled correctly, would have been the acceleration of B in the tangential direction. All right, so summation of forces in the normal direction, mass times acceleration in the normal direction. The normal direction is up and to the left, that right here. We're going to say that's going to be 20 newtons, but it's going to be minus our 9.81, right? That's going to equal 9.81 right here, but only right here, right? So we're looking at this right here, only times the cosine of that 30 degrees. And that's going to equal to our 1 kilogram times VB4 squared over our length. And they gave us a length. They better have given us a length. 1 meter. That was nice of them. So let's see. I have some call coming in, and let's see. Want to hear it on speaker? Hello? Yeah, that's me. Just 1 second. Idiot wanted me to do maintenance on my car, and but then they said Westbrook Honda is closed. Westbrook Honda is closed now on Saturdays, their service department. What the hell? I do it on a Friday? Well, I guess I could do it on a Friday. Anyway, 20 minus 9.81, but we have to do the cosine. Boom. Times, so we subtract, you get 11.5, so we're just going to take the square root. So we figure out that we're going to have 3.392 meters per second is what's going to happen at state 2, right? So now we could come down and use work energy. So we have KE1, no, not 1, let's say KE3 plus PE3 plus U3 to 4 is going to equal to KE4 plus PE4, right? Now we're going to have to set the datum here. Let's take the datum at 3 for this ball right here. So that means that this is going to be 0 right here. This is a conservation of energy. That's 0. So we can have 1/2 m ball v ball 3 squared is going to be equal to 1/2 m ball v ball 4 squared plus m ball g times y4 right here. Okay, and we're so here 1/2, our ball is 1. We want to know, this is what we're trying to find, is our VB3 squared. And this might be in a final exam question. Maybe it's the only final exam question. Maybe it's the exam 2 question. But if you have listened to this video, you would be able to kick its ass. But I'm going to turn this video off during the exam. You got to know how to do this problem. This is a great problem. Right there. Now we just found this 3.392 squared plus, here's the ball, 9.81. Now what's the height of this thing? Well, it's going to be this change right here. So this is the height that we're going to want to have right here. So that's going to be actually the length of this, which is 1 times 1 minus the cosine of 30 degrees. All right. So let's do all of this. Let's plug these in. I already have that into my calculator. That's why it's nice. Boom. By 2. So that's 5.75 is this right here. And then we're going to take the cosine of 30 right here, but subtract out 1, but I don't need negative. So that's going to be with that times 9.81. And we're going to add those two things together. Then we're going to multiply by 2, apparently, and then take the square root. So the velocity of B3, I don't know why I wrote 2 there, is going to be 3.759 meters per second, right? So it is more down at the bottom than it is at that instant that we're talking about. Okay, so now we have the velocity of right here at this point. So now we want to do is, we have to be careful here because of the angles, right? So this is going to be right here equals, but remember that is in this direction right there, right? So this thing is actually going to be caused like the impact would actually cause some tension. Like if we were going to draw, that's right in there. You could see that it's going to be there's actually going to be some impulse in that direction. But let's just ignore that for right now. But that could influence some of this actual behavior that's taking place. But anyway, we're going to have a velocity right here. This is going to be the ma times the velocity at A2 right here, right? Impact, we're going to pretend like these are frictionless right here, I guess, but it could potentially cause a thing here. And then we don't know if this is going to keep going this way or not right here, but it's constrained that it can only go in that direction. This one can only go in this direction. So this is going to be MBVB3 right here, but we want to do it we want to find it right here in this direction. So this thing is at a 20-degree slope right there, so I didn't do a great job. I drew it like it was almost 45 right here, but I think that angle, this right here is going to be the complement. Is that true? Let me see. Is drawing through down there. No, this would be 20 degrees and that would be 20 degrees. So this right here would be 20 degrees. Yeah, that makes sense right there, right? Okay, so that right there is 20 degrees. So we write out that the mass times velocity A2 is going to be equal to, and this is in the normal direction right here, is going to be mass of A, velocity A3 plus, because we're going to call that positive, this is the normal direction, that's the tangential direction, let's say. And so this is going to be right here, velocity B3, but it would only be the cosine of that right here, right? Cosine of 20 degrees of that component, because that would have the component right in there. So this is a 2 VA2 is going to be equal to 2 VA3 plus 1 times our 3.759 times the cosine of 20 degrees right in here. So we're going to be left with an equation 2VA2. I'll just keep it onto this side right here. 2VA3 plus whatever this turns out to be, 20 cosine times right here. So this is 3.533. Okay, but now we use the coefficient of restitution onto here. And we know that we have, let's see, the coefficient of restitution is 0.8. So we'll say 0.8. I'm just going to put numbers into this. And it's going to be V, whichever way we want to do it just be as long as we're consistent onto this thing, right? Okay. We have V B3 minus VA3 divided by VA2 minus VB2 right here. We know that this is 0, right? So because this thing right here is not, this ball has not moved right here during this time. And I got a little thing here, double checking. Boom. And what else do we have? B3, we know this right here. So we have this as 3.759 VA3, right? So that's going to be MAVA3. We don't care what that's going to be, right? We don't care about that thing. This is what we're trying to get at right here. Divided by VA2. So what we would like to solve this for here is 0.8 times VA2 is going to be equal to 3.759 minus VA3. So this is like equation 1 and equation 2 that we have. We want to get rid of VA3, so let's solve one of them for VA3. I think I'm going to solve this one right here. So I'm going to say that VA3 is going to be equal to 2, but then we have we're going to divide through by 2, so it's going to end up, we could actually just look at there and say that we're going to have VA2 and then minus right here, and then I'll go ahead and subtract it so I don't have to write it down again. Right here, divide that by 2. Boom. We have 1.766. So this is our other, so we'll stick this back into here. So we'll have 0.8 VA2 is going to be equal to 3.759 minus this guy right here, VA2. All right, and I'm a little nervous about what direction it's going to be, but we'll see right here. Minus, this is minus, that's plus 1.766 right here. Okay, so let's see what VA2 is going to be. VA2 is, we bring it over here. Ooh, I don't like that it's minus. Let me see, I might have messed something up along the way, and I don't see it. One VA2 is coming down this direction, so I don't see quite see what I've messed up so far. Let me pause while I figure that out in this already long video. Oh no, okay, that was totally fine. That becomes positive over there because 1.8. Okay, so I am going to subtract out and then that's going to be 1.8 divided. Okay, so it's 1.107. Seems pretty small right here. That seems kind of small. 1.107 is going to cause, of this is going to cause, so I'm a little leery right here. This right here is VA3. Yeah, we plugged in this right here. So I rewrote this thing out. So solve for VA3 right here, and divided through by 2 in the process. And then this guy moved over to here, and we had to divide by 2, so that's landed there. I'm okay with that. Then we put this into here, substitute it back into here, and So, okay, so this right here is going to become 1.8 when this thing goes back over on adds to there, and this, but that's plus that. That's why. All right, so 3.759, 1.766, and then divide by 1.8. Boom. Okay, I'm going to buy that a lot more. There are new items in your inbox. That's great. Thank you. Okay. Yes. So I will buy that as an answer for the velocity here at the bottom of this. All right. But now we have to do work and energy. So in terms of my layers, I've gotten to this point right here. So I've been able to find what the velocity of 2 is at the bottom. So now I focus onto the block, and so we have the KE1 plus our PE1, right? And that's going to be potential energy, all right? So then we're going to have the work between 1 and 2, which is going to be the friction, and the kinetic energy at state 2, and plus the potential energy at state 2. Now we're going to treat the potential energy here as 0. We know this guy right here. Kinetic energy here is going to be 0 at the beginning because the thing is going to be pushed up against the spring. So we have potential energy here. Let's just write the thing out. Potential energy 1/2 K, and they're calling it X, so that we'll leave that as X squared, plus the MA, and that's going to be MAG. Now the distance that this thing is going to, the distance and the height from here to down to there is going to be D plus X times the sine of 20. So D plus X sine of 20 degrees, and I didn't need this bracket right here. All right, so that's going to be the potential energy right in here. The amount of expended energy here is going to be negative coefficient of friction. Well, not coefficient of friction. We need to actually do a little FBD, IBD little thing right here, right? And this is X prime and Y prime, and we'll get our normal frictions coming up that way, weights coming down here, the weight of A, we have the mass times acceleration of this is the mass of A, acceleration of A onto the thing in that direction right there, but we just do the sum of the moment, sum of the forces in the Y prime direction is going to be 0 right there. So we find that the Fn minus WA times, and this is the angle, that's the 20 degrees right there, cosine of 20 degrees, right? It's equal to 0. So Fn is going to be 2 times 9.81 times the cosine of 20 degrees, and 9.81 times 20 cosine times, we get 18.44 newtons. Coefficient of friction is 0.2. 1.844, no, 18.44, wow. Keep doing it. And then 0.2 times, we're going to end up with 3.687 newtons, okay. And that's going to be times the distance x plus d. Okay, so we're going to have, we know everything we need to do, right? So, and we know what D is going to be. D is 1.5 right there. Okay, so let's plug all these things in here. Ignoring the KE, and the PE is 1/2 spring constant 800 times our x plus 1.5. And that's, oh yeah, we also need the plus our 2, 9.81, the x plus 1.5 times the sine of 20 degrees, right? And then minus my 3.687 times my x plus 1.5. And that's going to equal to 1/2, 2, and we'll establish what the velocity was at the base, 3.069 squared. Okay, so we have a lot of numbers to work through. So we can have 400 times x, sure, plus 400 times 1.5. 600, right? Plus, so we're going to have 9.81 times 2, okay, 19.6 times that, times sine of 20. Right, so that's going to be 6.71 times x plus, so we have the same thing times 1.5. So we get 10.07. We're going to subtract out negative 3.687x, and then, but that's going to be minus 3.687 times 1.5. So that's going to be a minus of 5.531 right here, and then that's going to be equal to 3.069 squared times 2 divided by 2, 9.419. Okay, so now let's get, oh wait, darn, squared. Can't do that. Gotta do a little bit more math. Shoot. So let's figure out what this is. This is going to be x squared plus, I always hate these things, x squared plus 1.5 times 2. Yeah, so 3x, right? Plus 1.5 squared, or 2.25. Is that true? I think so. And that all of these are times 400, right? So we have 400x squared plus 1200x plus that times 200, or plus 900. This is probably where I made a mistake in doing this right here. So it's x. Yeah, I'm pretty sure I got that right. Okay. Now we can go over through the whole thing. So we have 400x squared plus, let's get all the 12, so we have the 1200. Let's get all the x's, 6.71 plus, so that didn't do much. And then we're going to subtract out 3.687. So there's not a whole lot of difference right there. Let's see, 1203 right there, right? So actually, this one is really dominating the x part of that thing. And then lastly, and sometimes I expect this to be a negative right there, so we got to be a little careful. I usually expect that to be negative, but I don't see anywhere I would have made a mistake. All right, so now we have the, let's take our 900 and our add 10.7, sure, and then subtract out 5.531, and then also subtract out our 9.419, and I get a positive 895.8, and it all equals 0. Double check here, 900, so 910.7, subtract out there, subtract out this. I believe this. Now I want to find x. So it's negative b, negative 1203, that's concerning, plus or minus the square root of 1203, minus 4 times 400 times 895.8 divided by 2 times 400. So what's inside the square root? I usually do that first, and I go, that's times 400 times 4, boom. All right, that's supposed to be squared, dummy. All right, so let's make sure that that is a positive number. Yes, it is. And so I'll rewrite this out. Just doesn't hurt anything. Plus or minus. So that's the square root of that, and so that becomes 1,000. No, it comes 100. Ooh, this is scary. That's scary. Why is that negative? Something messed up. Something got messed up along the way. What could it be? Let me see. Let me check it again. 1203 squared. All right. 400 times 895.8 times, subtract it, take the square root, 118.0 divided by 2 and 400. This will always be a negative number no matter what. Can't be a negative number. So I messed something up somewhere. Where could it be? Pause. What a great video. It's kind of foolish. All right. So this should only be x squared. Right? That's the only amount. I don't know what I was thinking. All right, so I really made that more complicated than it needed to be. So none of that actually takes place. Yeah. So maybe this should not be a problem here that we're doing the thing. So let's get rid of all of that mess, all of this mess. All right. Yeah. I think I'll be able to solve it now. So let me gather all these x's, this x and that x. So that should be just 6.71 minus 3.687. Boom. Right in there, and no other x. So that's a 3.023. Okay, I'll buy that. And so now for this, we take a 10.07, subtract out 5.531, and then subtract out our 9.419. Boom. So we do get a negative number here. That'll help us, 4.880. 4.880. So now let's take our B, 3.023, 3.023, and our A is 400. Let's hope that's going to be enough. But this, oh, we got a negative, so that's good. 4.880. So that's going to make that so that it was not going to be negative underneath there. And here's our 400 right here. So here's our negative 3.023. And that spring would be really, really compressed if it was the entire time. Okay. Okay, so what's underneath here? we're going to take that squared and 4 times that and 400 times that, and take the square root. So we get 8.841, and this is still over 400, right? Yeah. So we know it's going to be the positive, it's better be the positive value, 3.023, subtract out, divide by 2, divide by 400, and we get close to the published answer. Okay, and the other answer, by the way, is going to be 3.023 and 8.841 divided by 2 divided by 400. But this is going to be a negative 0.01483. But here is what the answer is going to be. And I double checked, and that's what, at least that's what Chegg says it's going to be down here at the end. But I don't like his approach and explanation. It's all over the place. And although you can think, but mine's all over the place. Whoever wrote that one decided to jump back and forth and leave things in the square root. But anyway, not going to ask this one on an exam, but it would be a pretty interesting and exam. So let me see, how long did that take me? That's a 40-minute video that no one will watch. But if you did, tell me. I'd like to hear about it.